Hello, this video showcases the design, development, and testing of our autonomous mobile robot, highlighting key functionalities and system performance. The work reflects the combined effort of all team members, each playing a key role throughout the project. The following two sections outline the system capabilities on autonomous navigation and task execution in simulation and physical testing. While the team had sufficient time outside the lab to develop and validate navigation and simulation where the system is fully functional, progress within the physical robot was delayed due to hardware issues involving the Raspberry Pi and SD card. Although these issues were eventually resolved, the resulting 5-week setback significantly reduced available lab time. Consequently, a number of these requirements in the following two sections were only partially fulfilled or remained unmet during physical testing. Requirement 1 states that the robot must remain within operational boundaries. Since autonomous navigation was not fully functional, the robot could not stay within boundaries unless manually controlled. However, in simulation, it did stay within limits even when targets were placed outside the boundaries as shown here. Requirement 1 also specifies that the robot must localize its starting position. This was successfully achieved by the physical robot. A comparison between the robot's actual position and orientation in the environment and its representation in ARVIS indicates accurate localization, confirming that the robot correctly identified its starting pose. Requirement 2 states that the robot must detect obstacles within 10 meters. Testing showed that the LiDAR reliably detected wide obstacles up to 13 meters, meeting the requirements with 100% success rate. However, Requirement 2 also specifies a minimum clearance of 0.1 meters from obstacles, which was not achieved. Due to the lack of autonomous navigation, the robot could not maintain this clearance as a result. Requirement 3 states that the robot navigates within 0.2 meters of its intended path while avoiding collisions. As with previous requirements, this was met in simulation but not on the physical robot due to incomplete autonomous navigation. In summary, you can see that the operational area navigation requirements were all partially met. Next is autonomy and task completion requirements. Requirement 1 specifies that the robot must initiate operational tasks within 5 seconds of being powered on. As demonstrated in the video, after pressing the power button, the system status LED begins blinking green, indicating initialization, and transitions to solid green once ready. On average, this process took 46 seconds, meaning the requirement was partially met. Requirement 2 states that the robot explores and maps the operational area. Similar to previous navigation requirements, this was met in simulation but not in the physical robot. Requirement 3 states that the robot must determine its position in the environment. As with Requirement 1 in operational area navigation, comparison between the robot's actual location and orientation and its ARVIS representation indicates accurate localization. However, since the exact position values, x, y, and orientation, could not be extracted from the robot software, this requirement is considered partially met. The final two requirements relate to the overall system integrity. As the subsystems were not fully functional, the robot was unable to complete the task for even one colored object, nor could it complete all assigned tasks within the 20 minutes time frame. Next is object detection requirements. Requirements 1 and 2 states that the robot must detect unidentified color spins in the environment. The screen recordings shown use the developed object detection algorithm and represent 6 sample cases, tested over 10 runs per color. The algorithm successfully detects blue, red, yellow, and orange bins, but fails to detect purple and green. For classification, blue, red, and yellow are correctly identified, while orange is misclassified as red. Since only 3 colors are required and 3 are correctly identified, these requirements are considered fully met. And here are the calculations for both requirements. For requirement 3, the robot was initially required to measure each bin's dimension. However, since all bins now adhere to fixed standardized sizes, this step was removed from the algorithm to reduce computational load. Requirement 4 states that the robot shall identify the color of each object. To increase task reliability, object colors were limited to blue, red, and yellow. These were correctly identified in 100% of trials as shown. Requirement 5 states that the LEO rover must detect obstacles at 1 meters to allow time to stop. In testing, the vision algorithm reliably detected colored blocks at 0.5 meters, limited by the uncalibrated depth camera. Although this is below the required range, it still provides over 2 seconds to stop at a top speed of 0.25 meters per second. Formal range testing was incomplete due to limited lab time, and the 0.5 meter result is based on earlier unrecorded trials. The last 3 requirements are regarding objects grasping. In the video demonstration, the manipulator begins in its sleep position before smoothly extending toward a 20-gram sample block, opening its gripper to the full 0.07 meters span. As it approaches, upon contact, the gripper closes to 0.03 meters, securely grasping the block, then lifts and retracts back to the original pose before reopening to release the object. Note that, due to a delay in our hardware delivery, the payload sled shown here was kindly provided by a neighboring team. We integrated it with our own manipulator and control code. Therefore, these requirements are fully met. Requirement 7 states that the robot shall match each picked up object with the corresponding pin color. In this demonstration, the manipulator successfully places the red block into the corresponding red pin using the same payload sled. Due to time constraints, we were only able to validate this behavior with the red block and could not test with other colors before the presentation. Therefore, this requirement is considered partially met. Here is a summary of the full object detection requirements. Next is safety requirements. Requirement 1 states that the robot emergency stop button will stop the robot within 1 second of activation. We have deployed a program to manually control the robot, which includes a stop button. In this video, the forward button was held for a while, then the stop button was pressed. The robot immediately stopped. Also, the LEO rover has a built-in hardware emergency stop button located near the battery. Safety requirement 2 states that the robot's maximum speed must not exceed 250 mm per second during initial testing. To meet this, we implemented a speed limiting function in the code. As shown, when a forward velocity command exceeding 250 mm is sent, such as 1 meter's example here, the robot automatically limits it to 250 mm per second in the x direction. Requirement 3 states that the robot shall be manually manipulable. This was successfully achieved. The robot can be easily carried in the event of a power loss, and manual movement was tested both and without power. Requirement 4 was fully satisfied. We ensured that all components of the robot are securely enclosed and tightly connected, minimizing the risk of unexpected incidents. Requirement 5 was met successfully. The entire box, with all add-on, is easily liftable by one person, indicating it is under 20 kilograms. Also, the assembled robot can easily be lifted by a single person, as shown here. While a scale was not available, the LEO rover weighs approximately 6.5 kilograms, and our payload with all add-on, based on the sum of its components, it is estimated to be under 5 kilograms. This brings the total maximum of roughly 11.5 kilograms, confirming the requirements is met within the margin. This concludes the safety requirement section, all of which were successfully met. The last section is the hardware requirements. In terms of requirement 1, the entire robot was built based on the LiRover 1.8 developer kit and integrated with all specified accessories and add-ons, ensuring complete functionalities. Requirement 2 states that the robot design shall ensure no extension cables are chained. As shown in the images, cable routing is tidy and secure, with no tangling or chaining. Only one external cable, an Ethernet wire, was used, and it was routed safely through a designated exit point. We found the creative solution by routing the Ethernet cable through the chassis cutout originally intended for wheel clearance. Since our operational setting is a flat field, this space was not needed for mobility and was repurposed for cable management. Subsequent connections for the camera, manipulator, and LiDAR were made externally. Requirement 3 specified that the shielding must provide flexibility, durability, and be made of abrasion-resistant materials. The core of the board is composed of extruded polystyrene foam, a lightweight and rigid material. This core is sandwiched between two layers of white clay-coated paper, which offers a smooth, printable surface. While the rest of the robot is constructed from abrasion-resistant materials, the use of polystyrene foam and the clay-coated paper means the requirement is only partially met. Requirement 4 simply states the robot will use the Pinterex 150 gripper. And requirement 5 is about using the RB LiDAR A2M12 in the LiRover. Finally, requirement 6 is about using the Intel RealSense depth camera. As a summary, we can see that most of hardware requirements were met successfully. This concludes the requirements of our robotic system design project. We hope this video has given you a clear insight into the progress we have made this year. Thank you for watching.